Hi everyone, this is Professor M. Science, and today we will derive the energy eigenstates of a general two-state quantum system in another one of our videos on rigorous quantum mechanics. Two-dimensional state spaces feature in many important quantum systems, from spin one-half particles like electrons all the way to qubits from quantum computers. This video is pretty straightforward. We're simply going to derive the energy eigenstates of a two-state quantum system. There's also a companion video that's linked below where we calculate the eigenvalues of a general two-state quantum system. And I actually encourage you to watch that one first, so make sure that you do it if you haven't checked it out yet. So let's go! Today we discuss two-state quantum systems. And we're going to start by considering a general Hamiltonian H and its eigenvalue equation. As usual, these are the eigenvalues and these are the eigenstates, and both are labelled by a plus-minus subindex to indicate the two energy levels of a two-state system. In the companion video, we considered two different ways of representing the Hamiltonian H of a two-state system. First, the Hamiltonian can be explicitly written in terms of its matrix elements, like this. And to ensure that the Hamiltonian is Hermitian, we must have that the diagonal elements h11 and h22 are real numbers, and that the off-diagonal elements are the complex conjugates of each other. With this form for the Hamiltonian, the two eigenvalues are given by this long expression. Second, we can also write the Hamiltonian in the basis spanned by the identity and Pauli matrices like this, where the parameters d are the expansion coefficients. We can also rewrite it in this more compact form by defining the vector d like this, and the vector of Pauli matrices like this. Also, to ensure that the Hamiltonian is Hermitian, the d parameters must be real scalars. With this alternative form for the Hamiltonian, the eigenvalues are given by this expression, which can also be written in this more compact form. These two expressions are equivalent, and we derive both in the companion video. Depending on the situation, one or the other may be more convenient, and you will often find yourself using either form for the Hamiltonian of a two-state system, so it's a really good idea to become familiar with both. But let's go back to today. The aim of today's video is to derive the eigenstates of a two-state quantum system. And to do so, we will use this second form of the Hamiltonian in the basis of the identity and the Pauli matrices. So let's write down the eigenvalue equation that we're trying to solve. As I've just mentioned, in today's video we will use the expansion of the Hamiltonian in terms of the identity and Pauli matrices, and in this language the eigenvalue equation takes this form. Rearranging, we get that d dot sigma acting on the energy eigenstate is equal to the eigenvalue times the eigenstate minus d0 sigma 0 acting on the eigenstate. As sigma 0 is the identity matrix, this term here simply gives the eigenstate, and we end up with this expression. This quantity here is a scalar, which we will call lambda plus minus. This result shows that operating with d dot sigma on the Hamiltonian eigenstates gives a scalar times the eigenstates. And that means that the eigenstates of the Hamiltonian are also eigenstates of the operator d dot sigma, and the eigenvalues differ by a constant d0. Overall, this result implies that we can focus on the operator d dot sigma to determine the eigenstates of the Hamiltonian, and therefore in the rest of the video we will focus on this new eigenvalue equation where I'm omitting the plus-minus subindices for simplicity. As we will focus on the operator d dot sigma in the rest of the video, it is convenient to first write it out in matrix form. Let's first recall the form of the Pauli matrices, starting with sigma 1, then sigma 2, and then sigma 3. Using these expressions, we can expand the operator d dot sigma as a sum over a term proportional to sigma 1, a term proportional to sigma 2, and a term proportional to sigma 3. And we can then trivially add these three terms and obtain this matrix expression for the operator d dot sigma. To make progress, it is helpful to make a change of coordinates. So far, our operator here is characterized by the vector d, which is explicitly given by these three parameters. We will now change to a new set of three parameters, which we're going to call d, theta, and phi. These new parameters are defined as follows. We take d1 to be equal to d sine theta cosine phi. Then we take d2 to be equal to d sine theta sine phi. And we take d3 to be equal to d cosine theta. From these relations, we can also calculate the inverse transformation, but we're not going to need them today, so I'm not going to discuss them in detail. If you are interested though, you can always try to calculate them yourself. And for example, you should find that d is equal to the magnitude of the vector d. Now, at this point, the change of coordinates may appear a little bit arbitrary, and I get it. But I'm afraid that for now, you'll just have to trust me that it will eventually prove helpful, and we will be able to justify this better a bit later on in the video. So moving on, with these new variables, we can rewrite our operator d dot sigma. The element 1, 1 is just d3 up here. So using this relation, we end up with d cosine theta. From the element 1, 2 up here, we first have d1, which using this relation gives d sine theta cosine phi. And then we have minus I d2, which using this relation for d2 gives minus I d sine theta sine phi. And we can build the rest of the matrix in a very similar way, and feel free to double check this result. Next, we can rewrite the off-diagonal terms of the matrix. To do so, we first copy the 1, 1 element. For the 1, 2 element, we take d sine theta as a common factor, and we also take d sine theta as a common factor for the 2, 1 element, and we copy the 2, 2 element as is. Remembering Euler's formula, we see that this term here is the exponential of minus I phi, and this term here is the exponential of I phi. So, overall, we conclude that we can write the operator d dot sigma as equal to d cosine theta, d sine theta e to the power minus I phi, d sine theta e to the power of I phi, and minus d cosine theta. And this is the new form of the d dot sigma operator in terms of d, theta, and phi. To find the eigenvectors, we need now to diagonalize this operator. To do so, we're going to consider the corresponding characteristic equation, which is given by this expression here. Looking at the argument of the determinant, we can explicitly write out the d dot sigma operator minus lambda times the identity matrix. Now, if we evaluate this expression, we end up with d cosine theta minus lambda, d sine theta e to the power of minus I phi, d sine theta e to the power of I phi, and minus d cosine theta minus lambda. This means that we need the determinant of this expression to be equal to 0. And remember that the determinant of a 2 by 2 matrix is simply the product of the diagonal terms minus the product of the off-diagonal terms, and we need to set this to 0. To simplify this equation, we first rewrite the first product by taking an overall minus sign out of the second term. For the second product, first note that the exponentials cancel here, and we can then combine the remaining terms to obtain this expression. And all is still equal to 0. Let's now make a little bit of room, and let's copy the polynomial equation that we have to solve to find the eigenvalues. The first product here has this general form, which evaluates to a squared minus b squared. We can therefore expand the first product like this, minus d squared sine squared theta, all equal to 0. Rearranging, we get that lambda squared is equal to this expression. Finally, note that the sum of cosine squared and sine squared is equal to 1. And so overall, this implies that the eigenvalues lambda are equal to plus minus d, which we can also write as plus minus the magnitude of the vector d. By this point, you'll probably have noticed that we could have actually derived these results in a much simpler manner. If you remember from the beginning of the video that the eigenvalues lambda are related to the energy eigenvalues via this expression, and if you think about the companion video of eigenvalues, we also know that E plus minus is given by this relation. So we could have immediately deduced that lambda plus minus had to be equal to this expression. But I think that having gone through this derivation again will prove helpful, as it's allowed us to become familiar with the new parameters d theta and phi, and this should also make it easier to evaluate the eigenstates that we're going to tackle next. So let's now turn to the eigenstate psi. And let's start with the eigenstate associated with the lambda plus eigenvalue. In this case, the eigenvalue equation takes this form. And we can also write it out in matrix form like this. And this column vector represents the eigenvector. Applying the usual rules of matrix multiplication to the left-hand side, we get this for the top entry, and this for the bottom entry. And the right-hand side doesn't change. We can now compare the top entries here and copy down the equality explicitly. The d terms cancel here, here, and here. And so rearranging, we move all the terms involving the psi1 component to one side, and all the terms involving the psi2 component to the other side. At this point, it's useful to remind ourselves of the trigonometric identities known as the double angle formulae. If you know these identities, great, and if not, you can look them up in most tables, including those on Wikipedia or on Wolfram Math World, and you've got the links below. Specifically, we first need the equation for the cosine of an angle alpha, which is equal to the cosine squared of alpha over 2 minus the sine squared of alpha over 2. Considering this term on the left-hand side, we can copy it down, and using the double angle formula, we can rewrite it like this. Using another very well-known trigonometric identity, that sine squared plus cosine squared equals 1, we can combine these two terms into sine squared of theta over 2. And we end up with 2 sine squared theta over 2. The second double angle formula that we need is that the sine of an angle alpha is equal to 2 times the sine of alpha over 2 times the cosine of alpha over 2. And if we look at this term on the right-hand side, we can copy it down. And using the double angle formula, we can rewrite it as 2 times sine theta over 2 times cosine theta over 2. Right, so let's now make some room. And let's quickly copy the latest results that we got, which involve both the equation relating the two eigenstate components and the rewriting of each term through the use of the double angle formulae. Inserting this expression into this term, and this expression into this term, we can rewrite the condition that the eigenstate components must obey like this. We can now cancel this factor and that factor, and we can also cancel out a term sine of theta over 2 from both sides here and here. We end up with sine theta over 2 times psi1 plus equal to cosine theta over 2 times e to the power of minus I phi times psi2 plus. Finally, from this equation, we can rewrite the eigenstate psi plus. To make sure the equation is obeyed, we can choose psi1 plus as equal to this term, and we get this top entry for the column vector, and we can choose psi2 plus as equal to this term to complete the column vector. So, we've just found that for the eigenvalue lambda plus, the corresponding eigenstate takes this form. We could repeat the same exercise to determine the eigenstate associated with the eigenvalue lambda minus. And I won't go over the derivation in detail, but I recommend that you give it a go as it is good practice. You should find that in this case, the eigenstate is given by this expression. Great. This and this are the two eigenstates of this operator d dot sigma. But remember that the Hamiltonian operator obeys a very similar eigenvalue equation where the eigenstates are the same as those of the d dot sigma operator, and the eigenvalues are simply related to those of the d dot sigma operator by this expression. And so this means that we can immediately conclude that for the energy eigenvalue E+, given by this expression, the corresponding eigenstate can be written like this. And equally, for the E- eigenvalue, we have this associated eigenstate. And so that's it. These are the energy eigenstates of a general two-state quantum system. Ta-da! Let me add a comment about the mathematical derivation that we've just gone through so that we can better justify the change of variables that we made from the original D1, D2, and D3 Hamiltonian parameters to the d, theta, and phi parameters that we've been using in most of this video. To really understand the usefulness of this change of variables, you should note that the final eigenstates are given in terms of trigonometric functions of theta over 2, for example here and here. And if we try to write the eigenstates directly in terms of the original d parameters, the mathematical expressions would look actually really complex. By contrast, they look actually quite neat in terms of these new theta and phi parameters. And absolutely the same thing applies if we try to work directly with the Hamiltonian in terms of the matrix elements rather than the d parameters. So overall, when working with the energy eigenstate of a general two-state quantum system, it really is most convenient to work in terms of these expressions that feature the theta and the phi parameters. However, it is also really interesting to mention that most quantities of interest in quantum mechanics actually don't really directly depend on the eigenstates, but instead they depend on quantities that are built by combining the eigenstates, for example in the calculation of the expectation value of some physical observable. And it turns out that for most quantities of interest, such as expectation values, the final answers actually don't depend on the theta over 2, but only depend on simpler functions of the theta and phi variables. And so as a result, the final answers themselves can be easily transformed back in terms of the original d parameters or in terms of the original Hamiltonian matrix elements. So what does all of this mean? In practice, for you will usually use these expressions for the eigenstates in terms of theta and phi for your intermediate calculations. But at the end, you will likely be able to write your final answer in terms of the original Hamiltonian parameters. We have a few videos looking at examples of two-level systems in the links below, so do check them out to see all of this in practice. To finish, let's make sure that we have an orthonormal set of eigenstates. Let's start with a normalization. For psi plus, we need to evaluate this norm. In the matrix formulation, we get this row vector multiplying this column vector. Note that the entries in the row vector involve the complex conjugates of the corresponding column vector, which leads to the change of sign in this phase factor. Following the usual rules of matrix multiplication, we have the product of this term with this term, which gives this expression. And then we need to add the product of this term with this term, which is simply sine squared of theta over 2. We can cancel this exponential with that exponential, and so we end up with the cosine squared of theta over 2 plus the sine squared of theta over 2. And this, of course, is equal to 1. So our initial psi plus eigenstate was already normalized, which is great. I would now encourage you to repeat this same exercise to confirm that psi minus, as we wrote it, is also normalized. And spoiler, it is, but it's nice to double check. Finally, we can also check orthogonality, which amounts to checking that the overlap between psi plus and psi minus is equal to 0. To finish, we have the final expressions for the eigenvalues and eigenstates of the Hamiltonian of a two-state quantum system. As a final note, remember that we can always multiply a quantum state by an overall phase factor without changing the physics of the problem. And therefore, you may often encounter these eigenstates written in one of many possible alternative forms. But you should always be able to relate them back to these expressions that we've derived today. The energy eigenstates of a general two-state quantum system take a particularly simple form in terms of trigonometric functions. With these results, you can now tackle any quantum problem that's defined in a two-dimensional state space. And we have several examples in the links below. As always, I hope that you liked the video and please subscribe.